This video will discuss question 25. In figure 1, several options are shown how to possibly add diodes to the circuit of figure 4 in order to stabilize the oscillations. If we are interested in the least possible harmonic distortion, which option should we use and from which node should we read the oscillation signal? We can already eliminate some options by looking at the answer from question 24. In that question we found that D13 and D14 will never activate. Moreover, we found that D7 and D8 will cause this oscillator to become unstable, so that cannot be the correct answer. We also learned that the diode pairs D9, D10 and D11, D12 will activate at the same time, so these might be an option. Since D9 and D10 have an impact on the operation of this inverting amplifier, let's investigate what happens when one of these two diodes turns on. The first thing that we should recognize is that this terminal here should be at 0 volts because this non-inverting terminal is grounded. That means that one of these two diodes will only turn on if Vc is at a voltage larger than 0.7 volts or smaller than negative 0.7 volts, because these diodes are modeled as ideal switches, and they have a threshold voltage of 0.7 volts. The gain of this inverting amplifier, A, can be given as negative R5, which is the resistance from the output to its inverting input, over R4, which is the resistance from its inverting input to the input of this inverting amplifier configuration. If one of these two diodes were to turn on because Vc exceeds the threshold voltage, that would cause this R5 to be in parallel to a short circuit. So R5 is in parallel to 0 ohms. As an effect, the gain of this inverting amplifier will become 0. So when the amplitude of our oscillating signal becomes too large, the gain of our inverting amplifier, and as a result the open loop gain of our oscillator, will decrease. From that we can conclude that the introduction of D9 and D10 causes this oscillation to be able to oscillate at a constant amplitude. Part of the question that we should find out is at what node we should measure to see as little harmonic distortion as possible. The frequency-dependent network, consisting of these three RC sections, is effectively a bandpass filter with its peak around the oscillation frequency. Because harmonic distortion typically lies at multiples of the oscillation frequency, we can conclude that this node here should actually contain the least harmonic distortion in the entire circuit. And since this operational amplifier functions as a buffer, VB will also contain very little harmonic distortion. Vc, however, lies at the output of this inverting amplifier with the nonlinearities caused by these diodes. And it's typically nonlinearities or non-idealities of this operational amplifier which causes harmonic distortion to be introduced to the signal. Vc most likely does not contain the least harmonic distortion. So we can now eliminate multiple answers. For example, we would prefer not to read from Vc because Vc does not contain the least harmonic distortion. We knew that D8 and D7 cause the oscillator to fail, D13 and D14 never turn on, and we know from our previous analysis that D9 and D10 do cause this oscillator to become stable. So this must be the correct answer. D9 and D10 and read from VB. VB is at the output of the unity gain buffer, which mirrors the output of our bandpass filter.